Hello and welcome to 11.8a of Edexcel's Year 13 A-Level Maths course, Pure Half. So we're looking here at integration, finding areas under curves using integration. And I've split this subchapter into two parts, 11.8a and 11.8b. You could be asked to find areas underneath or between curves, which are given parametrically as well in terms of parametric equations. I'm going to deal with that separately in 11.8b. So here we're going to be finding areas underneath curves and between curves using integration where the curves themselves are not given parametrically. So here we're looking at more standard type questions where we need to find areas between the x-axis and the curve or between two given curves or functions. So I'll explain as we go through, but before that, of course, you can probably guess by now there's some warm-up questions to attempt. I've put two on here today. So the first one is SUVAT based, the other is about radians, arcs and sectors. So pause now and have a go at these on your own, press play when you're ready to see the solutions, and I'll guide you through how to get the answers in case you're not too sure how to make a start. Okay, so let's have a look together at warm-up question 1. So question 1, we have two cars A and B moving in the same direction along a straight horizontal road. So first of all, we're told at time t equals 0, they are side by side, passing a point 0 on the road. So this O, or 0, can be the origin, essentially. Now, what we could choose to do here is to picture this using a distance time graph for the two cars A and B. So we know at time t equals 0, they're side by side. So if I just get here a distance time graph ready, it now says car A travels at a constant speed of 30 meters per second. So I'll put t equals 0, they start here, and then car A travels at 30 meters per second. So on a distance time graph, that's going to be a straight line. It's traveling at a constant speed, no change of speed, so no acceleration. So on a distance time graph, that will just be a straight line with constant gradient, something like this. Distance is increasing in equal steps per unit time. Car B, however, passes O with a speed of 20 meters per second, so it starts off slower because 20 is obviously less fast than 30, but also it says it's got a constant acceleration of 4 meters per second squared. And so car B, its distance will increase slower to begin with, but then as it accelerates, it will eventually start clearing distance at a faster and faster rate. And so the graph for car B would look curved, something a bit like this, where eventually the green curve for B will overtake the curve, the straight line for A. And this point here, where they intersect, that's going to relate to where the cars cross over. That's going to be where car B overtakes car A. First of all, though, we just need to calculate the speed of B when it's travelled 78 meters from the origin. So essentially, for this one, we can use SUVAT. So for part A, let's just consider what we've got and what we need from SUVAT. So we're talking about car B here. So it's travelled 78 meters from O, and so we can put that the displacement is 78. Its initial speed, U, is 20, so we can put 20 there. We want the speed after it's travelled 78, so I'll put the speed as V, as a question mark. That's what we want to find. The acceleration is 4, and we don't know the time, nor are we interested for part A in the time. And so what equation of motion relates the top 4 variables and doesn't require t to be known? Well, this one here, I'm hoping you can remember, or if not, it's in the formula book, in fact. We're going to use v squared equals u squared plus 2as for this one. So v squared, this is what we're trying to find, is going to be u squared, which is going to be 20 squared, plus 2 multiplied by the acceleration, which is 4, multiplied by the displacement at this point, which is 78. So if you use your calculator for that, you should hopefully find that v squared is 1024. So therefore, v will be the square root of 1024, which gives 32 meters per second. So that's the speed of B once it's travelled 78 meters from the origin. For B, what we need to now do is find the distance O to A when B is 78 meters from O. So now we're thinking about car A. So just think about car B again for a second. So just for B, now we know that it's got a final speed of 32 meters per second when it's 78 meters from the origin. And here we're talking about the same point. We could actually work out the time taken for it to get to this speed of 32 meters per second. So what we can do here for B, we can consider V equals U plus AT, another Suvat equation. Rearranging for the time taken to get to 32 meters per second will be V minus U, the change in speed, divided by the acceleration. So it's gone from 32 meters per second from 20, a change of 12 meters per second, and the acceleration is 4, and so that gives 3 seconds. So in other words, when B is 78 meters from O, that's 3 seconds after they've been travelling where they were head-to-head. And so therefore, now we know it's 3 seconds of travel, we can then plug in for A, how far it's travelled in just 3 seconds. So therefore, for A, we can use S equals UT plus a half AT squared. But of course, A is travelling at a constant speed of 30 meters per second, so it's not going to be accelerating at all. So this half AT squared, we don't need to consider because it's not accelerating. So simply the displacement of A will just be its initial speed U multiplied by the time taken, which we now know is 3. So for car A, it's travelling at 30 meters per second for 3 seconds. Therefore, when B is 78 meters from O, A will be 30 times 3, which is 90 meters from O. So at this point, 3 seconds, A is still ahead of B. So we're looking maybe somewhere like this for 3 seconds. So I'll just add this on to give a bit more sort of clarity in terms of this graph. So I can say here, that might be T equals 3. For part C, we need to find the time when B overtakes A. So the time when B overtakes A, let's just call this T here. And that's going to happen using this graph at this point here. That's when T will equal T, capital T. That's what I'm trying to find. And so clearly, they'll cross again when the times are equal and their distances from O are equal too. So I can set S for displacement, but because they're both going in the same direction, I can just think of this as distance. We set S for the distances equal for both cars. So I'm going to set S of A, distance of A, equal to the distance of B. So for particle A, or car A, you need to get used to thinking of particles, it's just simply S equals U times T. So it's just basically going to be 30 multiplied by T. Then the displacement of B is going to be the initial speed of B multiplied by the time. So that's going to be 20 T plus a half multiplied by the acceleration of car B, which is 4, multiplied by time squared. So that's going to be times T squared. So this will now neaten up. I now have 30T equals 20T. Half of 4 is 2, so I've got plus 2T squared. Rearranging, I get that 2T squared minus 30T from both sides minus 10T equals 0. Divide by 2 and then factorize, and I'll get T minus 5 equals 0. So they're going to be level with each other when time is 0, which we've already got, or when capital T is 5. So therefore, we can see we're going to overtake when time is 5. So therefore, B overtakes A after 5 seconds. And so therefore, we've done the first warm-up question. Let's now have a look at warm-up question 2. So for question 2, we've got a diagram showing triangle ABC, with AB being 8, from A to C is 11, and BAC is 0.7 radians. So the arc BD, where D lies on AC, so D is somewhere on the straight line AC, we're told it's an arc of a circle with a centre A and radius 8 centimetres. The region R, which is shaded here, is bounded by the straight lines BC and CD and the arc BD. So first of all, for part A, we need to find the length of the arc BD. Now this is an equation and we need to remember. The length of an arc, I'll just put in the arc first. The arc from B to D is this curve, so we'll add this on in blue. The formula for the length of an arc, L, is the radius multiplied by theta, where theta is the angle in between the two radii comprising the arc. So the radius, R, is 8, and the angle theta in radians, it needs to be in radians for these formulae, L equals R theta, and area being half R squared theta, needs to be in radians. So we're told this is in radians, which is good, so therefore theta is 0.7. Plugging these values into this equation here will give us that the arc length is going to be just 8 multiplied by 0.7, which of course gives 5.6. So the arc length is 5.6 centimetres. Part B, the perimeter of R, is what we need to find next, giving answers to 3 significant figures. So R, I'm going to just colour code in yellow and bound with BC and CD like this. So BC is a black straight line and CD is the purple straight line. So the perimeter is just going to be the area enclosed. So the perimeter is going to be the length which encloses this area. So the perimeter is going to be the blue arc plus length BC plus CD. If I write it in the order BD plus CD plus BC, I can now populate what we've got. So BD will just be 5.6. From C to D will be 3, because that's going to be 11 minus 8. And then BC, I'll explain now as I show it, is going to be this. So BD 5.6, CD is just 3, which we get from doing 11 minus the 8, which I'm just explaining here. That just becomes 3, of course. And BC, I've got by using the length of the triangle using the cosine rule. So if I consider the overall triangle ABC, then the length BC is going to be obviously 8 squared plus 11 squared minus 2 times 8 times 11 times cosine of the angle in between. So this is an application of a cosine rule for finding a length. That's all I'm doing there. I'm not going to go into any more details on this. This is GCSE, so just get your head around this on your own if you're not sure where this has come from. This is just cosine rule, okay? So if you just compute this and give the answer as required to 3 different figures, you should end up with 15.7 once it comes out on the calculator and you've rounded it correctly. Part C now, we need to find the area of R, this shaded bit in yellow, again giving answers to 3 significant figures. This shaded part here, we need to think of as being the area of the entire ABC minus this sector from A to B to D. In other words, the area of R is the area of a triangle minus the area of the arc. So if I colour in the arc in blue from A to B to D, I can just imagine this yellow area as being the triangle overall minus the blue. So the area of a triangle, of course, is half AB sine C. That's this formula here. So triangle ABC, I've used this formula for the area of a general triangle, half AB sine C, where angle C is the angle in between the two known sides, 8 and 11. This here, sector ABD, I'm just applying the formula for the area of a sector when we know the angle in radians. The area of any sector with an angle of theta is a half radius squared multiplied by the angle, in our case 0.7. Again, if we put this into the calculator and round correctly and just take a bit of care, we should see that the area of R drops out to be 5.95 square centimetres. Now we're suitably warmed up, let's talk about the main part of this lesson, which is finding areas using integration. So first of all, how to find areas under curves using integration. Well, in year 12 we saw how integration can be used to find areas enclosed by curves and straight lines. This concept can also be extended to find areas enclosed between two curves, which we're going to come on to next. But again, we need to remember from year 12 that when we integrate to evaluate an area which lies underneath the x-axis, that will come out to be a negative value. When that happens, we just need to take the absolute value of that. So the area, if it's underneath the x-axis, is the modulus of the value obtained when we integrate between limits where x is underneath the x-axis. So let's get straight to a worked example. So worked example 1, we have this curve here, shown the diagram, where we've got y equals 9 over root 4 plus 3x, and we need to find the area of region R, which is enclosed by the curve, the x-axis, for line x equals 0, which essentially is the y-axis, and of course the x-axis down here. So we need to use integration, to find the area of R. So using this idea of finding the area underneath a curve and the x-axis, we can say that the area R will therefore just simply be the integral in between 4 and 0 of this function. So I'm going to write it as 9 over root 4 plus 3x with respect to x. 9 is a constant, so I'm going to choose to write this on the outside of the integral. And 4 plus 3x, underneath on the denominator all square rooted, I can write in index form as 4 plus 3x to the power minus a half dx, in between the limits of 4 and 0. So in terms of how to integrate this, you should be able to do this fairly slickly now, but just in case, I'm going to show you how you could do this using a u-sub, in case you have forgotten for any reason. So what I'm going to suggest we might want to do is we call this u. So I'll show you how to do this now using a use substitution in case you've forgotten or just need a recap. It can't hurt to. If you're okay integrating that yourself, by all means you can skip ahead on this video. This is just if you need. So if I just let u be 4 plus 3x, then du by dx, differentiate u with respect to x, that will just give 3. So therefore, dx in terms of du, dx is going to be du divided by 3. So therefore this integral here, I can change. It's going to become 9 lots of the integral between 4 and 0 of now u to the minus a half, and now dx I can replace with du over 3. So that will allow us, get my teeth in, to neaten up this quite a lot. So du over 3, so that 1/3 I can take to the outside. So then 9 times 1/3 just gives me 3 here. I'm just getting from 4 to 0, u to the minus a half du. And that will then become 3 lots. If I increase this power by 1, I'm going to get u to the positive a half. Then I divide by the new power. So if I divide by a half, it's the same as multiplying by 2. Then of course plus c if needed. But because here I'm integrating between definite limits, I don't need to do that. And so essentially this is just going to become 3 lots of 2u to the positive a half. So just putting this here, that's going to be 3 lots. And 2u, well, u, of course, is just 4 plus 3x. So we're going to put that back in to the power of a half. In between the limits, of course, now 4 and 0. So now just put the limits in. So when x is 4, this is going to become 4 plus 3 times 4, which is 16 to the power half, which is the square root of 16. But if I then put the lower limit of 0, I'm going to get 2 lots of 4 plus nothing to the power half. So 4 plus nothing is just 4 to the power half. That's going to be the square root of 4. So then simplifying, square root of 16 is 4. 4 times 2 is 8. Square root of 4 is 2. 2 times 2 is 4. So it's just 3 lots of 8 minus 4, which is 3 lots of 4, which of course comes out to be exactly 12. And so our first example, the area R is equal to 12. Next, integration to find areas between curves. Very similar indeed. So if I just have a picture here to illustrate, to find an area in between 2 curves, for example, if f of x is like the upper curve and g of x is the lower, we could find the area underneath f of x, which of course is just taking the integral of f of x in between a and b. If we did that though, that would include all of this area, including this bit here underneath g of x. If we just want r, we'd therefore need to subtract away the integral of g of x in between the same limits of x. So, put simply, we just use this formula. Area of R between the limits b and a is going to be f of x minus g of x integrated with respect to x, which, if you wanted to, could be separated into 2 integrals. The integral between b and a of f of x minus the integral between b and a of g of x. So, let's have a look at a couple of examples using this. So, work to example 2 firstly. We have a diagram to the right showing the curves y equals f of x and y equals g of x. F of x is sine 2x, and g of x is sine x cos squared x, where x is ranging from 0 to pi over 2. So region R is bounded between these 2 curves. Use integration to find the area of the region R. So using the result which we've just seen, we can hopefully now therefore see that this area is going to be the integral between pi over 2 and 0 of f of x minus g of x. With respect to x. So f of x first is sine 2x, and g of x is, which we're minusing off, is sine x cos squared x. So this isn't going to be too bad to integrate. Sine of kx, that's a standard result. This one here, sine x cos squared x, this is going to be essentially an application of the reverse chain rule. Sorry, reverse product rule rather. So if I just show you how to do this now. So sine 2x, sine actually integrates to minus cos. So we're going to have minus cos 2x. However, because of this 2, we therefore divide by 2 when we integrate it. So we're going to have minus 1/2 cos of 2x. This bit here, though, I'm just going to put to the side and show how this would integrate if we needed to use a u sub, for example. So let's just picture the integral of sine x cos squared x dx. So I would prefer to use a u sub for this. If I call u cos squared, so cos x rather, I can then take du by dx. cos differentiates to negative sine. So therefore dx in terms of du will just be du divided by negative sine x. So this integral is going to become sine x times u squared multiplied by du all over negative sine x. The sines now, of course, will cancel on the top and the bottom. So then we're just going to have the negative, because that minus sign, of the integral of u squared du. And so that will then give us, when we take the integral of negative u squared du, that's going to give negative 1/3 u cubed. Then, of course, if needed, would be plus c. So in other words, when we integrate this bit here to get the integral of minus sine x cos squared x, if we integrate obviously sine x cos squared x, we get minus 1/3 what u cubed is, plus or minus c. But because we're taking a definite integral here, we don't need to worry about the c. So if we integrate sine cos squared x, we get a minus thing, but because we're minusing off this here, it actually will become a positive. So we're going to get plus 1/3 u cubed. If u is cos x, then of course that's going to be cos x cubed, or cos cubed x. And of course we don't need plus c now. So just take this between the limits of pi over 2 and 0. So if we input the limits first of all, so pi over 2, cos of 2 lots of pi over 2, cos pi, again use your calculator if needed, in fact I would say use it, that gives minus 1. So we've got minus 1/2 minus 1, and then I'm going to have plus 1/3 of cos cubed of 90. Well, cosine 90 is 0, so that's going to give just 1/3 of 0, which is 0. Then minus off the lower limit when x is 0. Well, cosine of 0 is 1, so cosine of 2 lots of 0 is still 1. So this is going to give minus 1/2 times 1, which of course is negative 1/2. Then plus 1/3 times cos of 0 cubed. Well, cos of 0 is 1. 1 cubed is 1. So this just gives 1/3 multiplied by 1 cubed, which is just 1/3. So minus 1/2 times minus 1 is 1/2. Minus this. Now minus 1/2 plus 1/3, that will actually simplify overall to being minus 1/6. So minus and a minus also makes a plus. So 1/2 plus 1/6, 4/6. 3/6 plus 1/6 gives 4/6, which is 2/3. Let's have a look at one more worked example, question number 3. This one here was actually an exam question, which I thought was really nice to show. So this one, we've got a diagram to the right showing a sketch of 2 curves with these equations. So the first one's y equals kx squared, and the bottom equation is y equals a root of kx. Again, x is bigger than 0 for each, and k is some positive constant. This region here, R, shown shaded, is bounded between the 2 curves. We need to show that for all values of k, the area of R is independent of k and is always equal to 1/3. How strange is that? Well, let's see if we can prove it. What I do need is to find this limit here at the upper end. So obviously x is going from 0 here, but what's this one where they intersect? So to find where they intersect, let's just first of all set kx squared equal to root kx. So we're going to intersect either C. when kx squared equals root kx. So if I just square both sides, that will give me k squared x to the 4, and root kx all squared just gives kx. Now if I divide both sides by k is a positive constant because we're told it, so we're allowed to do this. So dividing both sides by k, and I get that kx cubed equals x. Rearrange and take x from both sides. Kx cubed minus x equals 0. Factorize out the x. Whoops, that's going to give me, sorry, k to power 4. I'm only cancelling a k, that'll be k to power 4, my bad. So that becomes power 4 as well. So now I'm going to get x, brackets, kx cubed minus 1 equals 0. So therefore, either x is equal to 0, which we've got here, or kx cubed minus 1 is equal to 0. So at this point here, that's when kx cubed minus 1 equals 0. So therefore, x cubed equals 1 over k, which equals k to the minus 1. So therefore, at this point here, x is going to be the cube root of k to the minus 1. And the cube root of k to the minus 1 is going to be k to the minus 1/3. So at this point, x is going to be equal to k to the negative 1/3. So using that, we can now find the area R. So R is going to be the integral in between 0 and k to the negative 1/3 of the function which is the higher one, which is going to be root kx. So I'm going to rewrite this in a different form, in fact. So root kx, I'm just going to put as k to the half, x to the half. So it's going to be that minus kx squared. With respect to x. Now these functions here aren't too bad to integrate at all, actually. So k to the half is just a constant, so that's going to stay as it is. So x, the power of x is obviously going to increase by 1, so we're going to get x to the 3 over 2. Then we divide by that new power. So dividing by 3 over 2 is the same as multiplying by 2/3, but I've obviously got this here. So I've got k to the half times by 2/3 x to the 3 over 2. Then this one here, k squared obviously integrates to 1/3 k cubed. So this bit here, when integrated, will give me 1/3 kx cubed. In between the limits, where x is going to be k to the negative 1/3, and the lower limit when x is going to be 0. So it might be slightly messy, but it should drop out okay. So if we just input this now, the upper limit, k to the half, is just going to be obviously k to the 1/2 times 2/3. Now if I put in here x being k to the minus 1/3, to the power 3 over 2, that's actually going to give me a power of a power conundrum here. This is going back to GCSE. We'll simplify this in a moment. I'm going to minus off 1/3 of k Now, when x is k to the minus a third, k cubed will just give k to the minus 1. And of course, for lower limit, when x is 0, well, that's going to give nothing there, and then k times 0 cubed again will be nothing. So I can just focus on the upper limit here. So what I'm going to have now is k to the half times 2/3. So power of a power minus 3 on the top, 6 on the bottom. So I'm going to get k to the negative 1/2. I'll just try and separate this top line away so I'm not going to get in the way. Then I'm going to minus off 1/3. K times k to the minus 1 will just become a third, because k to the 1 and k to the minus 1 cancels. In the same way, this is going to happen here. K to the half times k to the negative half will cancel too. So it just actually becomes, after all of this, 2/3 minus 1/3, which just becomes 1/3. So that's been shown quite exhaustively. You might be able to skip some of these steps here with your substitutions, but essentially that is why we get 1/3. So it's independent of k. As you can see here, k cancels because of these powers as given as such. So hopefully you're more primed now to try some of these questions on your own. On that note, if you could skip to 315 to 317, exercise 11H in the blue book for year 13. So I'd suggest to try questions 3 through to 7 and then 9 through to 11. There are some questions where you need to find areas using parametric equations within this chapter. I'm going to focus on those in the next video, so fear not. Try these for now. If you get stuck, let me know, and keep going and don't give up. So until next time, it's goodbye for myself.